Hi, welcome to class. My name is Don Lafond, Professor Don, and this week in Cisco 1, we are covering Module 11 IPv4 addressing. I've broken this topic into 3 separate videos. The first will introduce you to IPv4 addressing. The second video will talk about subnetting, and then the final video is on VLSM, virtual length subnetting. So sit back, relax, and enjoy the video. If you've got any questions and you're here with me live, please ask your questions at the break in between videos. If you're watching it as a recording inside of NetAcad, please ask your questions in the help discussion forums. And if you're watching it as a YouTube video, please ask your questions down below in the comments, and I'll be happy to help you with those, with your answers. Anyways, let me go ahead and start the share my screen first. Share my screen. Start. Let me move a little bit of stuff I gotta do first. Gonna move this guy over here and start the presentation. And we are set. So again, Module 11, IPv4 addressing, Part 1. So in this video, we are going to calculate an IPv4 subnet scheme to efficiently segment the network. That's the module objective. In this video, we're going to cover IPv4 address structure, the unicast, broadcast, and multicast addressing, and types of IPv4 addresses. In the following 2 videos, we'll talk about network segmentation and subnetting an IPv4 address. Let's go ahead and get started. Again, I'm going to describe the structure of an IPv4 address, including the network portion, the host portion, and the subnet portion. I'm going to compare the characteristics and uses of the unicast, broadcast, and multicast IPv4 addresses, and I'll explain public, private, and reserve IPv4 addressing. The IPv4 address structure. So binary number and the binary numbering system consists of just zeros and ones. Those are called bits. An IPv4 address is expressed with 32 binary bits divided into 4 8-bit octets. Let me zoom in on this. So this is what a computer sees. For the network, it sees a series of ones and zeros broken down in chunks, if you will, of a byte of 4 bytes, 4 octets of 8 bits. And for IP addressing, each host, each host on the network has an IPv4 address designed in just ones and zeros. That's all the computer sees, just ones and zeros. Of course, if we were going into each address and we had to literally type all these ones and zeros for setting an IP address on a router port, for example, that would be cumbersome, and it would be a good chance to make an error in our typing. So we don't have to do that. What we do is we do dotted decimal. So IPv4 address is allocated or assigned or represented is the best word, represented as dotted decimal in IPv4. And for example, PC1 has the IP address 192.168.10.10, a whole lot easier than all those ones and zeros. The network address is 192.168.10.0, and the gateway would be 192.168.10.1. Talking to, looks like an ISP and a different network, 209.165.200.225. So a lot easier again than ones and zeros, okay? That's why we use dotted decimal. So we have to be able to convert between binary and decimal. And so I have a video here that shows this conversion process.
In this video, I'm going to discuss binary to decimal conversion. But before I do this, I want to take a look at positional notation, or place values. I have the number 2,168 here. If we look at the place values of the number 2,168, we can see that the place values have the ones place, the tens place, the hundreds place, the thousands place, 10,000, 100,000, and million. These are the place values of the base 10 decimal number system. You can see that we have the number 2 in the 1,000s place. So we have 2 1,000s. We have a 1 in the hundreds place for 100. We have 6 in the tens place for 60. And we have 8 in the ones place for 8. So effectively, we have 2 1,000s, 1 100, 6 tens for 60, and 8 ones for 8. Now, when we're talking about the place values in the decimal number system, we're talking about the powers of 10. You can see that the ones place is the 10 to the 0, the tens place 10 to the 1, the hundreds place 10 to the 2, or 10 times 10, which is 100. The thousands place is the 10 to the 3, or 10 times 10 times 10, and so on and so forth. So you can see that the place values are based on powers of 10. If we look at the number 2,168 then in long form, we can see that effectively we have 2 1,000s, 1 100, 6 tens, and 8 ones. And 2,000 plus 100 plus 60 plus 8 totals 2,168. This is the type of counting and addition that we learn as children. The decimal system is base 10. It's based on the fact that you have powers of 10, but more importantly, you have 10 characters or 10 numerals in this counting system, from 0 all the way up to 9. So that means that in each place value, you can have anywhere from the number 0 up to the number 9. In other words, if I had the number 9,168, I'd simply replace the 2 here with a 9, and now I have 9 1,000s totaling 9,000 in the 1,000s place. So in any one of these place values, you can have the number 0 all the way up to 9. This is the base 10 decimal number system. If we consider binary and look at it in the same light as decimal, binary is a base 2 number system. There's only 2 characters or 2 numbers, 0 and 1. So under the place values, we can only have zeros or ones. The place values go from 1, which is 2 to the 0, to 2, 2 to the 1, 4, 2 to the 2, 8, 2 to the 3, or 2 times 2 times 2 is 8. 2 times 2 times 2 times 2 is 16. That's 2 to the 4th power, place value of 16. The 32's place, the 64's place, and the 128's place. Notice that I extended the table to 8 place values. That's because 8 bits is an important grouping of numbers. 8 bits makes a byte in computer processing. So now I have the place values for essentially 8 bits. If I want to write the number 168 in binary, I just have to find the corresponding place values and plug in either a 1 or a 0. So I'll go to the 128's place and ask myself, do I need 128 to reach 168? Yes, I do. So I'll put a 1 there. Now, do I need a 64? I already have a 128. If I add 64, I would get 192 because 128 plus 64 is 192. So the answer is no, so I put a 0. I still have 128 now. Now, do I need a 32? 128 plus 32 is 160. So yes, I could use a 1 here. Now I have 160. Do I need a 16? No, that would make 176, which would go over my target number of 168. I'll put a 0 here. What about an 8? If I add an 8, I'll hit the number perfectly. 128 plus 32 plus 8 is 168. I'll follow this up with zeros in the 4's place, the 2's place, and the 1's place. And 168 in binary equals 101,01000. I now have 128. I have 132. and I have 1/8, and 128 plus 32 plus 8 equals 168. If we go to the next slide, you can see now that I'm now charged with converting the number 0, 1, 1, 0, 1, 1, 0, 1 to decimal. If I want to go the opposite way and convert this binary number to decimal, all I need to do is plug it into the place values. I'll put it in here, 0, 1, 1, 0, 1, 1, 0, 1, and then add it up. I have a 64 and I have a 32. 64 plus 32 is 96. Plus I have an 8, that makes 104. Plus 4 makes 108. Plus 1 makes 109. This number converted to decimal is the number 109. Now let's look at a full IP address in binary. I'll go to my next slide. And you can see in this next slide, I now have a 32-bit IP address, 4 octets, or 32 bits total. If I want to convert this binary IP address to decimal, all I need to do is count up each individual octet. Let's start with the first one right here. We can see that 1, 1, 0, 0, 0, 0, 0, 0. 128 plus 64 is 192. Now, the next octet has 10101. Let's do that one. 0, 1, 0, 1, and then all zeros. If we count up the numbers, 128 plus 32 is 160, plus 8 is 168. The next octet is all zeros with a 1 in the last place in the ones place. This is easy. This is the number 1. All zeros and a 1 in the ones place makes the number 1. And then finally, we have a number here. I'll plug it in here to my table. And I have the number 011000101. We can see that 64 plus 32, we've already said, is 96. Plus 4 is 100. Plus 1 is 101. So the conversion of this binary IP address to decimal is 192.168.1.101.
So that's actually a repeat of a video we saw earlier in the semester when we were talking about conversion. I thought it was important before we really start talking about IPv4 addressing to go ahead and repeat that video. So hopefully that was just a refresher. Now, these next few slides just basically say what that video said. The first step in a conversion process is to put down our placeholders. Radix is how they identify it here. In this case, ones, tens, hundreds, and thousands, if we're talking about decimal. We do this every day, at least we used to, when we're counting the money in our pockets. How many 5s, how many 20s, how many 50s you may have had. So you're familiar with this. Well, we do the same thing in in decimal. You put down your table 1, 2, 4, 8, 16, 32, 64, 128, and then you just determine how many of each you have, and that gives you your number. In this case, we have 1, 128, and 164. That gives us our 192. Fortunately, there are other ways to convert these numbers that in your head. I mean, as we practice, you're probably not going to be drawing out a table trying to determine how many ones and zeros to convert. You will probably be able to do this in your head, but drawing out the table doesn't take long to do. So if that's what you need to do at first, that's what you need to do. Now, here they show, and remember when we're talking about dotted decimals, we have 4 octets. Each octet, we have to convert those ones and zeros for. So in this case, all we did was convert the first set on that previous slide to 192. We had 128 place, 164 place, and the rest were zeros. We would then plug this, each succeeding octet into our table to determine each succeeding decimal or dotted decimal notation number. And what we're doing here is we're actually using a logic where we take our number and we basically plug it in. And we say, do we have any 128s? If we do, we put a 1. Do we then have any 64s? If we do, we put a 1. If we don't, then we say no, and we add a 0, and then we go to 32s. And they give you examples for breaking down the entire address. So this 192.168.10.11, the 192 is 110.0.0.0.0.0. 168, this is the numbers that would add up to 168. So 101011. Sorry, 10101000, and then 10, and then 11. An IPv4 address has 32 hierarchical addresses that make up a network portion and a host portion. And it's important for you to understand how the computer goes about figuring out what part is the network portion and what part is the host portion. And so you have to look at that 32-bit stream. Remember, the computer just sees ones and zeros, and you have to take the network portion and compare it to the subnet to make that determination of where that break is between the network and the host portion. To identify the network and host portions of an IPv4 address, the subnet mask is compared to the IPv4 address bit for bit from left to right. The actual process used to identify the network and the host portion is called ANDing. Now, what ANDing does, before I get to ANDing, they show you subnet masks here. And in this case, 255.0.0.0 is all, 255 is all 8s, so I mean all 1s. So all 1s in the first 8 bits or octet, and then zeros for the rest. It's /8 in CIDR notation. Now, CIDR notation is also called slash notation. In today's world, we hear it more as slash notation. And CIDR itself stands for classless interdomain routing. This is the only place in Cisco 1, 2, or 3 that they tell you what CIDR stands for, because it's just basically not used, that term. You're not going to be referred to it as, oh, in slash, not 25 CIDRless, classless interdomain routing. You're not going to hear that. You're going to hear CIDR notation /notation /26. And note, when we have a /24, it's 24 ones. When we add a 1, we're borrowing from the host portion. We have /25, and that actually gives us 2 networks. I'm not going to get ahead of with subnetting right now for you, but basically, just again to tell you that 25, 26, 27, 28, we're just counting the numbers of ones, and we take that those numbers of ones in the subnet, and we place it, our subnet mask, we place it under our IP address, and then we are able to AND the 2. That's what the computer does. You could do it as well to make the determination. Again, it's much easier to do it in other ways. But you could AND the IPv4 address and the subnet mask to determine the network. I have a video to show you that in a few minutes. But when I say and, the logical and is a Boolean operation used to determine the network address. A logical and is a comparison of two bits where only a 1 and a 1 produce a 1. Any other combination results in a 0. So if you have 1 and a 1, it's a true. If you have a 0 and a 1, or a 0 and a 0, or 1 and a 0, it's a 0. So all we do, all the computer actually does this, all it does is take the 1 and the 1 and get a 1. 1 and a 1 and get a 1. Everything else is 0 in the first octet. So we have zeros down below, 0 and a 1. Here we have all ones. So the 1 comes down, the 0 does not, 1 comes down, and we go all the way across with that. Now that's how we determine the network. Now, when I say network, there are three types of addresses in the IPv4 address structure. There's the network address, there's the host address or addresses, and then there's the broadcast address. Now, I'm going to zoom in on this, make it a little bit easier to see, and there is an error on this slide, and that error is this network. This is the 10 network. You can see they all are in the 10 network. We're in the 10 network. The 10 should be a different color, not the 0 here at the end. I guess actually 192.168.1 is the network portion. I'm sorry, 192.168.10 is the network portion, but we normally refer to it as the 10 network. So it's kind of odd to have the 0 as a highlighted item. But anyway, so we have the network address of 192.168.10.0. We have individual IP addresses for our router gateway address and each one of our host addresses. A switch doesn't really have an IP address, at least not on a port. It has switch virtual addresses, which are for remote access for SSH and Telnet. It has a switch virtual an SVI, a switch virtual interface to be able to talk to it remotely, but it doesn't show an IP address here, so it just hasn't been configured yet. Now, again, looking at the address in the subnet mask indicates that we have 816.24 zeros. That's why we have Saturn notation, / notation of 24. Then we have the network address. And we have first address that's usable and the last address that's usable, and then we have our broadcast address. That's a 24 network. It's not always that way. For example, if we had a 25 network, we would have half of the addresses, 128 addresses. The first would still be 0. It would be 192.168.10.0/25. And then the first address would be 1, but then the last address of a /25 would be 127. And the second network would start with 128 and it would go to 255. So that's why it's important to examine the CIDR notation, the subnet mask, to determine where the network ends and where the first network ends and the second network begins. All right, let's go to the next slide. I have a video that I need to play for you that will talk about this.
All devices on an IPv4 network need a 32-bit logical address in order to communicate. This 32-bit logical IPv4 host address consists of a network portion or network ID on the left and a host portion or host ID on the right. The length of these depends on the size of the network. Larger networks will have a longer host portion. A network can be thought of as a range of addresses. All devices on the same network have the same bit pattern for their network ID, but they will have a different host ID. Some addresses in this range are reserved and have a special name and meaning. For example, the first address in the range is used to identify the network itself and cannot be assigned to any host. It is referred to as the network address. The last in the range is called the broadcast address and is used to send a message to all devices on the network at once. It also cannot be assigned to any host. All the IP addresses between the network and the broadcast addresses make up the usable or valid host range and can be used to address the hosts on the network. Let's take a look at how these addresses are determined. In order to forward data, a device needs to know what network it's on. Using their host IP address, their subnet mask, and a process called binary ANDing, a device can find what's referred to as the network address. This address represents the network to which the host belongs and will be slightly different than its host IP. To do this, the device compares their host IP and their subnet mask bit for bit. If the bit values are both a binary 1, the result is a binary 1. If one or both of the bit values is 0, the result is a binary 0. Let's take a look at an example. Let's say we have a PC with a host IP address and a subnet mask of 192.168.2.38/24, and we'll use ANDing to find the network address of the host. Here's the host IP in binary. Here's the subnet mask in binary. If we compare them bit for bit, we can see that a 1 and a 1 results in a 1, a 1 and a 1 results in a 1, a 0 and a 1 results in a 0, a 0 and a 1 results in a 0, and so on until we have compared all 32 bits. Notice that the last octet is all binary zeros. Because we are using a /24 subnet mask, the first 3 octets represent the network portion, and the last octet is the host portion. Network addresses will always have binary zeros in their entire host portion, however long it is. In this case, the last 8 bits. If we convert to dotted decimal, we can see that this host belongs to the network 192.168.2.0/24. Now let's determine the broadcast address for this network, which is used to send a message to all devices on the network at once. Whereas the network address had all binary zeros in the host portion, the broadcast address will have all binary 1s. Since the host portion in this example is just the last octet, to determine the broadcast address, we keep the network portion the same and change the host portion to all binary 1s. This results in a broadcast address of 192.168.2.255. Next, we'll determine the usable host addresses, which lie between the network and the broadcast addresses. The first usable host in binary will be all binary zeros with a binary 1 at the end of the host portion. Converting to dotted decimal, this tells us the first usable host on this network is 192.168.2.1. Lastly, we'll determine the last usable host, which will be all binary 1s with a 0 at the end, the opposite bit pattern of the first usable host. Converting to dotted decimal, we get 192.168.2.254. Let's recap our calculations. We began with the host IP address of 192.168.2.38/24. Using binary ANDing, we determined that this host belongs to the network 192.168.2.0. Keeping the network portion the same, but placing all binary 1s in the host portion, we determined that the broadcast address for this network is 192.168.2.255. Again, keeping the network portion the same but changing the host portion, we determined that the usable host range for assigning addresses to devices on this network is 192.168.2.1, which is one number up from the network address, and 192.168.2.254, which is one number down from the broadcast address. You can see that our original host IP address falls within this range. Things to keep in mind when working with IPv4 addresses. All IPv4 host addresses are 32 bits in length. A portion of the address represents the network that the host belongs to, and that starts at the left. The remaining part is the host portion, which identifies the host on the network. And there are 2 special reserved addresses on every network that can't be assigned to hosts. One is the network address, which is the lowest in the range of addresses and represents the network that all the devices belong to. And the other is the broadcast address, which is the highest address in the range and can be used for a shout out to all devices on the network at once. Thankfully, there are shortcuts you can take for calculating these addresses without having to convert to binary first. But examining these addresses at the bit level should help you understand how network devices interpret them and also how the dotted decimal format is derived.
All right. Nice job there. Well done. So unicast, broadcast, and multicast. So when we're talking about unicast, you've got to understand that each device in the network, like printers, servers, and network devices like PCs, require a fixed IP address to communicate. It can be changed, and it will change most of the time. But hosts in a small network can also be configured with static addressing, where you go in and you determine the address, and you go into the configuration of your PC in this example, and you set your IP address and your subnet mask. You also must have a gateway in order for your PC in this case to be able to leave the network and reach out. If it was going to be assigned automatically, we would use DHCP. DHCP is not part of this lesson. We'll learn that later on. Most networks use Dynamic Host Configuration Protocol, DHCP, to assign IPv4 addresses dynamically. The DHCP server provides an IPv4 address, subnet mask, default gateway, and other configuration information. DHCP leases the address to the host for a specific period of time. If the host is powered down or taken off network, the address in use is returned to the pool. A good example of this is a college student brings his laptop to the campus. The DHCP server hands him an address, him or her an address. The student uses it for a period of time, then goes home. After a period of time, which could be hours or days, that address is released back into the pool. This is for IPv4. IPv6 doesn't generally use DHCP to keep track of addressing, although that is possible in IPv6. But generally speaking, we use Slack, and we'll get to that later. Again, I'm getting ahead of myself for IPv6 to create their own addressing. Yeah, we'll learn about IPv6 next week. IPv4 has three main types of sending messages: is unicast, broadcast, and multicast. Unicast is where one device sends a packet to one other device or a frame to another device. Think about a unicycle, right? Unicycle has one wheel. One packet goes from the source to the destination. Broadcast is one to all. And then there's also unicast in the 224 range of addressing. Unicast is one to a select group. For example, it might be all routers. In IPv6, that is a multicast address, is all routers or all nodes. Again, getting ahead of myself. Unicast transmission is sending packets to one destination. For example, PC at 172.16.4.1 sends a unicast packet to the printer at 172.16.4.253 to print a device. Broadcast, again, goes to all. So PC at 172.16.4.1 sends it to broadcast. Since this is a /24, notice that the destination is all ones, right? It's a broadcast message, as you saw in the previous video, and everybody receives that broadcast. A multicast transmission, again, 224, in this case 10.10.5, goes to some of the devices, but not all of the devices. Types of IPv4 addressing. Public IPv4 addressing are globally routed between Internet Service Provider ISP routers. As defined in RFC 1918, private addresses are common blocks of addresses used by most organizations to assign IPv4 addresses to the internal hosts. These are the ranges: 10.0.0.0/8, 172.16.00/12, 192.168.0.0.16. Now, public addresses. Why do we need private addresses? Well, we need private addresses because remember there were in IPv4 there's only 4.3 billion addresses. Well, I myself have probably more than 75 addresses in my home already with my smart home devices. So this allows our devices, hosts, for big and small corporations to have many addresses, thousands of addresses, yet only have one public address. So we'll get into the numbers, how many addresses are in a /8 or /12. Millions, I can tell you, millions, thousands, and hundreds. Again, remember, when we're dealing with a /24, for example, we only have 256 addresses, 254 usable. We'll get there. Private addresses are not globally routable. So your router will not propagate broadcast messages, but it also will not propagate private addresses outside. So you at your home can have a 192.168.0.0 network, and I can have it in my home as well. It's not a problem because the routers will not send those addresses out onto the internet. Here they just show you that private addresses are not routable, used only within internal networks, and they must be translated to a public route. That's called NAT. NAT is Network Address Translation, and it translates IPv4 private addresses in the 10 network, the 172.16 or 192.168 networks, out to public addresses in that 4.3 billion at private addresses. So our college, for example, has five public addresses, and it uses the 10 network to divvy out all of the networks through all of the campuses that we have and all of the computers and all the labs and the offices, etc. They take a 10 network and they chop it up into pieces, and we'll learn about subnetting in our next presentation. The edge routers are responsible. The edge routers are responsible for taking the private addressing and turning it into public addresses, one of those 5 addresses I was telling you earlier. There's also some special use IPv4 addresses. For example, a loopback address, it's in the range 127, so 127.0.0.1, and that's what you'll normally see. You'll see 127.0.0.1, or if you're creating 2 or 3 of them, you'll have 0.0.2, 0.0.3, but don't let any exam throw you off if they say, what address is 127.255.255.1? It's also, it could also be a loopback address. Those addresses are used to simulate, for example, in the testing environment, simulate the ISP. But in the real world, it can be used on a host to test your TCP/IP operation. So if you're home and you're not able to, if you're on your home computer or a work computer and you're not able to communicate with other people, you can find out quickly if it's you or if it's the network by pinging 127.0.0.1. If you get a response, then you're fine. It's probably fine. It's probably something outside of the network or your configuration to get outside of the network. You also have local link addresses. That they're commonly known as automatic private IP addresses. No, that's not what we call them. We call them PIPA addresses or self-assigned addresses. The only thing used 169.254. Whatever. That network range allows for Windows computers to communicate within their own network, but not outside the network. So let's say you have a classroom full of computers, all Windows computers, all connected to a switch, but you don't have a gateway set to be able to, or you don't have a router connected. The actual a PIPA addresses would be able to allow you to talk to the other computers even without a network address assigned, because they'll all assign in this range and therefore they'll be able to talk to each other. But how useful is that for a PC in the first row of the classroom to talk to a PC in the second row of the classroom. Not very useful, but it is. But they are assigned automatically. And then there's some test net addresses, 192.0.2.0/24, and they're used for teaching and learning. We generally see in our class 192.168, and we just use those addresses in that private range. But there are some test net addresses as well. Oh, what do we have here? We have pinging, showing pinging from pinging 127.0.01 and you getting a reply. That means that your equipment is working properly. Now, legacy, classful addressing. We still work in the ranges 8, 16, and 24, but we subnet those ranging. Subnetting off of the classful ranges is easier than it is when you're subnetting off of, say, a 23. You're given a 23, or I'll show you that later in another presentation. But anyway, so this is when when IP addresses, they weren't worrying about IP addresses. They could assign a company a Class B address, and it literally would have a Class B address would assign 65,000 hosts to the network. So they would receive, they would have to assign in batches of each of 16,000 networks would have 65,000 hosts, and that's how you had to break it down. You had to break it down. Each network had 65,000 hosts. If you were assigned a Class C network, you could have 2 million networks, all of them with 254 addresses. But what happens if you only need 300 addresses? Then you have to use a Class B network with 65,000 for 300 addresses. That didn't really make sense. So classful address allocation was replaced with classless addressing, which ignores the rules of classes A, B, and C because of wasting so many addresses. The Internet Assigned Numbers Authority, IANA, manages and allocates blocks of IPv4 and IPv6 addresses to the 5 regional Internet registries, RARs. Now, RARs are responsible for allocating IP addresses to ISPs who then provide the IPv4 address blocks to smaller ISPs and organizations. These are the 5 RARs, and they're pretty easy to recognize, except for RIPE. A for the Americas, LAC for Latin America, AFRINIC obviously for Africa, APNIC for Asian Pacific region. One student said, I remember RIPE using Russia. And it's like, okay, if that's what you got to do, that's what you got to do. But I always, up until that student told me that, I always just said the one that's left out is the one that's Europe. But Europe, the one that is Europe also includes Russia, which just happens to start with an R. Anyways, and RIPE, RIP, is Europe, the Middle East, and Central Asia. And that is it for the first presentation of my 3. Let me go ahead and stop sharing my screen, and I'll bring you back to me. All right, so again, my name is Don Lafond, Professor Don. Today, we covered in this video the first part of my IPv4 addressing presentations. There's 3 of them that I've created to really give you a deep overview of subnetting. The first one's pretty simple, just talking about IPv4 structure of the addressing. Now we're going to get, in the next video, we're going to get into subnetting. If you have any questions, please, I'm going to give you a moment. If you're live with me, I'm going to give you a moment to ask those questions. If you're watching this as a recording inside of NetAcad, please ask your questions in the help discussion forums. If you're asking it out on YouTube, please ask questions down below the video inside of the comment section. I'll be happy to help answer those questions, but please help each other. That's what builds a community. When you help each other answer questions, that's awesome, or help answer each other's questions, that's awesome. Also, please give me a check mark, if you will, to like and subscribe to my videos so you'll be notified when I release more videos. You'll be able to easily find me in the future as well. My pleasure to help you learn Cisco routers and switches. And in this video, IPv4 addressing that we will be applying to all of those pieces of equipment. So have a great day. Thank you. Enjoy learning. Enjoy your assignments this week. And I will see you again in the next video. Thank you for coming to class. And how do I turn this off? There it is. There we go. All right, great.